Here we are. All right. Welcome back. This is the review of the second one of the topics in this molecular thermodynamics course, and this topic is intermolecular forces. The material is taken from the fourth chapter of the Prausnitz book. So there are several parts in which this discussion is organized. The first, we talk about a little bit about generalities, and we introduce the electrostatic forces. So the one thing to remember is that these equations that we will be looking at, they are essentially models that we use to understand how different molecules interact with each other. They are models, so as a consequence, they will have a large number of assumptions that are built into it. But the whole purpose is to try to be able to eventually predict a vapor-liquid equilibrium, for example, just by knowing what type of molecules we have in the system. There is not a single model that at the moment works, so we are left with trying to do the best we can with what we have, and that sentence in blue is something that is important. So they are all models, some are bad, some are good, but the only way that we can identify a good model is whether or not we are able to get some useful information from it. So can it or can it not predict experimental results? In terms of nomenclature, we talk about interactions between molecules. In this schematic, we represent the molecules as spheres, and R is the center-to-center distance between these spheres. This symbol over here is for the potential between those two interactions, and this one here is the force. So what we assume is that at large distances, the potential goes down to zero. That is an assumption. As long as it's constant, it doesn't really affect anything what is the value of the potential at infinite, but it just makes our life easy if we assume that it is zero. The reason it doesn't affect much what is the value of this constant is that the force is described as minus the derivative of the potential with respect to the distance. So wherever you have a maximum in the force, you have wherever you have a maximum in the potential, the force is equal to zero. And wherever the slope of the potential is maximum, you have either minima or maxima in the forces. Now this part of the curve is obviously my hand that is not very firm when I write on PowerPoint, but anyways, you got the gist. The convention is that whenever the force is positive, there is a repulsion between the molecules, and when the force is negative, there is an attraction. So when we look at the potential like this, the two molecules will probably like to be one here and one here, because that is where the minimum of the force is, but actually they will probably like to be in this position here, which is the minimum of the potential. So that's basically what they want to be. And if they want to go from here to this other position over here, they have to overcome the maximum in the barrier. So there will be some event needed to occur, because otherwise the molecules will just be happy to be in their local minima. Okay. Sometimes systems get stuck in local minima that could, for example, this one here, that does not correspond to the global minimum, this one here. And we may need to wait for a very long time for those systems to evolve to the global minimum. Okay, now talking about forces, in general, what we wrote earlier was that the force is only a function of the distance, but in general, it is a function of the orientation of the two molecules. So the notation becomes a little bit more complex, and we need to take into consideration the relative orientation. However, the principles are the same. In general, what we need attractive forces is to explain the transition from a vapor phase to the condensed phase, for example. And many of the properties of the condensed phases, they are due to the attraction between the molecules. And that's because in the condensed phases, the molecules are very close to each other. The repulsion, however, becomes important because if you take a liquid and if you want to push it and reduce its volume, and the repulsion is what is providing this resistance to compression. By definition, configurational properties are those that depend on the interactions. So, for example, the specific heat of a gas at low pressure, the key is low pressure. At low pressure, there are not many molecules. So this specific heat is the amount of heat that you give to the system to increase its temperature. At low pressure, the molecules are isolated. So the heat goes in and it increases the vibration of those molecules, but it does not have anything to do with the interactions between two molecules. On the other hand, the energy of vaporization, that's the energy that you need to provide to a liquid to make it become a gas, that strongly is related to the interactions between the molecules, because when the molecules are strongly attracted to each other, they prefer to be in the liquid phase. If you were to look at the specific heat of a liquid, that specific heat will be a configurational property, because now you have all the molecules that are very close to each other. All right, so these were the definitions. And in the current literature one, I put this paper over here. It's just to stimulate your interest a little bit. And what you will see is that these people try to look at the behavior of crowds in social gatherings. So these social gatherings could be people walking on a pavement when there are a lot of people and everybody is moving in the same direction, in which case you can apply the fluid dynamics approaches. And on the other hand, they also were interested in what happens when you have a lot of people, for example, attending a show, or when you have a lot of people in a square and some unexpected event happens. Maybe they were specifically referring to events in the past few years where trucks ended up getting into crowds, and they were analyzing the aftermath of those events, because essentially the people were running away from the event and they were trampling onto each other. And of course, there were many people getting injured as a consequence of that. And essentially, they took away the personalities, the human aspects that is related to that, the panic and so on and so forth. And they showed that by describing the movement of the people as if they were soft solids, you can apply some theory to see what is the overall behavior and the collective movement of all of these people together. So, and of course, the reason I bring it up is that this word soft solids is telling us something about how these particles, so to speak, are interacting with each other. Anyways, this is just a paper there for you to take a look at, so that maybe you get a little bit excited about the capabilities of describing interactions between particles. Now, talking about interactions between molecules, the one type of forces that we know the best are the electrostatic ones. This is the electrostatic potential. This one here is the electrostatic potential. And where C is a constant, these two EI and EJ are the charges that are carried by two particles, and R is the distance between the two particles. See that we have a constant here, because when the distance is very large, the potential is going to be equal to that constant. By convention, we want the potential to go to zero. So when R, this R here, goes to infinity, this part goes to zero, the potential goes to zero, so we are finding that that constant is equal to zero. Notice that the potential is positive when the two charges are the same, and it gets bigger and bigger as the distance decreases. So that tells you that if you have two positive charges and they're getting closer to each other, there's going to be a repulsion between them that becomes stronger and stronger as the two particles get closer. On the other hand, when one particle is positive and the other one is negative, you're going to have an attraction. The constant C is described by this equation there, where pi is a constant, pi, 4 is a constant, and epsilon naught is the permittivity of vacuum, which is also a constant. It describes the properties of vacuum. If you do the minus the derivative of the potential with respect to the distance, you recover the force from this potential, and these will be the equations for the electrostatic force. And notice that it scales with the square of the distance, but everything else is the same as we just discussed. So the two positive charges are going to repel each other, one positive and one negative are going to attract, and two negatives are going to repel. You know all of these, you've done a lot of studies on this even in your high school periods. Now, the thing is that electrostatic forces are important, for example, for explaining why crystals like salt, sodium chloride, they have a very high melting point. If you do a Google search, you will find that the melting point of sodium chloride is on the order of 700 Celsius, if I remember correctly. And that's because these ions are strongly packed into each other. The crystal structure has one sodium, which is positively charged, next to one chloride, which is negatively charged. So they really like to be as close as possible because the interactions are driven by these electrostatic forces. So the question that I always ask is, okay, then what happens when we put this sodium chloride in water? And of course, I am Italian, so I do that very frequently whenever I cook. And the story goes that the sodium chloride is soluble in water. So the moment you put it in your pot of water, even when the water is not boiling, that salt is going to dissolve up to the solubility limit, of course, but the solubility limit is pretty high. So why is it that something that melts at 700 Celsius when it is pure becomes soluble in water at ambient conditions? If the interactions between two ions of that salt are described by the electrostatic potential. Well, the answer to that is water. And in fact, when you put charges in water, you have to modify that constant here, and you need to add another epsilon there, which is the permittivity of water, which is approximately, if I remember right, 80, 78 something. So essentially what that means is that the electrostatic forces becomes in water are 1/80th of what they would be in vacuum. And the reason for that is the moment you have an ion in water, it's going to be surrounded by the water molecules. And if you have the sodium ion that is positively charged, water has oxygen and two hydrogens, the oxygen is partially negatively charged, so you will have a lot of oxygens that surround your sodium. And on the other hand, around the chloride, which is negatively charged, you're going to have a lot of hydrogens. So that screening is what reduces the electrostatic interactions in water. Okay, the other thing that is important here is the range of interactions. So the potential scales with 1 over the distance. So if you double the distance between two molecules, the electrostatic potential between those two molecules is going to become 1/2. Okay? The range of interactions is important in simulations. You will see more as we proceed, because in simulation we need to take into consideration how each molecule is interacting with the neighbors. So when we have a short interaction potential, as in this case, we only have a few molecules that surround our little red sphere. But when we increase that interaction potential, as in this case over here, you notice that for the same system, it's just copy-pasted, but now all of a sudden we have many more molecules that we got to follow. So the overall interactions, the overall force that is acting on that red sphere is going to be the result of interactions that are due to all of these molecules over here, whereas here it was only due to this couple. Okay? So the range of interaction is important for computational purposes. It's also important for practical purposes. A few years ago, there was a debate. Actually, it was a discovery from Rice University. They found that when you take different materials, some hydrophilic, some hydrophobic, some differently hydrophilic, and you take one graphene layer, which is a layer of carbon atoms, and you deposit that graphene layer on the original materials, and you then put a droplet of water on top, the contact angle of water will not change much compared to when the graphene layer was not there. So effectively what that discovery did was to enable people to make materials with different wetting properties, but with a nice layer of carbons on top of it, and water doesn't like to stick on carbon, so it will be able to be removed quite nicely. And that has to do with the range of interactions, because the range of interactions are longer than the diameter of carbon atoms, so it is possible to extend those interactions across the graphene layer. Now, graphene is just one layer. Graphite is many graphene layers, one on top of the other. So this group in MIT, what they did was they conducted simulations, and they put different graphene layers near a droplet of water, and they were looking at what happens to the contact angle of that water. And what you see is that the contact angle was approximately 91 when everything was only one graphene layer, but it goes down to 78 when you have 3 graphene layers. So the graphene is still the same. It still doesn't like water too much, but now you have more of these layers, and the range of interaction between the carbon atoms and the water molecules is longer than these 3 layers of carbon, and as a consequence you have more attraction between those carbon atoms and the water, and the contact angle becomes less and less, a little bit less. All right, so that is a direct consequence of the range of interactions. Now, in the second part, I introduced dipole-dipole forces. So we have so far discussed electrostatic interactions that are those that we understand the best. We've done a lot of experiments. We know what the parameters are. We know where they come from and everything. The problem is that while ions are charged, many molecules are not, they don't carry a negative charge. They may have a partial charge on one portion of the molecule and another partial charge on a different part of the molecule, but the overall charge in many cases is actually neutral. So what we do in these cases, we identify the partial charge and we identify the distance between these two partial charges. And then we can identify dipole moments. One example is ammonia, for example, where the nitrogen is grabbing the hydrogens away from those, the nitrogen is grabbing the electrons away from those hydrogen atoms. So the nitrogen is ending up being a little bit negatively charged. The hydrogens are going to be a little bit positively charged. So you got a partial charge in the hydrogens, a partial charge in the nitrogen. The two partial charges are equal in terms of amount, absolute value, but they have different sign. So you got the dipole moment. And this is the definition of the dipole moment, which is just the product of the partial charges times the distance between them, and the unit is the dBi. Okay. For reference, in this table here, there are some dipole moments of a few molecules that are out there, and you go from carbon monoxide, which is about 0.1, all the way to water, 1.84 dBi, and then if you take ion pairs, you have dipole moments that are particularly large. There are many other substances out there. If you look at that table from the book, you will find a few other dipole moments. What's important for you to remember is that the big transition happens here when the dipole moment from below 1 becomes larger than 1. And the reason for the importance of that will come evident in just a couple of minutes. But keep it in mind that there is a wide range of molecules that have very different dipole moments. Now, we are talking about interactions between these dipole moments. So what we can do is to try to use our understanding of electrostatic interactions and to extract what is the potential between these two molecules. So what we do, we put one molecule here, and we put another molecule here, and we know what is R, which is the center-to-center distance between these two molecules. Now what we can do is define the relative orientation by these angles between the two molecules, actually between the two dipole moments. That geometric distribution tells us where this partial charge here is, these are the partial charge here, and these are the two partial charges. Now, by knowing where those four partial charges are, what you can do is to apply the description of electrostatic interactions between each of the partial charges, for example, this one, and those that are in the other molecule. And of course, the main importance of the relative orientation is that by changing the relative orientation, you are changing the effective distances between the various partial charges. So in some cases, you're going to have repulsions. In some cases, you're going to have attractions. When you combine everything, you can find that the overall potential for a given distance and for a given relative orientation is given by this equation over here. It's clearly a little bit complex, but it is a consequence of the geometric construct. So there is nothing particularly difficult in obtaining this other than keeping track of what are the real distances. What you see here is that there is a minus in front, there are the dipole moments of the two molecules, the I and J. All of these are cosine and sines. And then this is the distance to the cube in the denominator. These are all constants. This ends up to be a positive value. The dipole moments are positive. So what you find is that, well, in most cases this is positive. Depending on the orientation, it may end up being negative. But in most cases, what you find is that the dipole-dipole interaction is going to give you an attraction between the two molecules. Okay? And this attraction, the potential, scales with the product of the dipole moments of the two molecules. And that's where it's important to know if that dipole moment is larger than 1 or less than 1. Because when it is less than 1, that product between the two dipole moments will become even smaller. But when it is larger than 1, it will become bigger. So that's why that threshold becomes important. Okay? Now, in general, some comments regarding dipole-dipole interactions, they are going to have this is going to be the most energetically unfavorable configuration, where you have the partial charges of the same sign that are close to each other. On the other hand, this is going to be the most energetically favorable configuration, where you have the partial charges of opposite sign that are close to each other. So the result of this is that when we have dipole-dipole interactions, the dipoles, if they can, they want to be parallel to each other so that they can minimize the electrostatic interactions. On the other hand, what we have in every system is thermal energy. What the thermal energy tends to do is to rotate these dipole moments. So there is going to be a competition between these two effects. At large temperatures, the disorder wins, and you have a lot of systems that move around, and the dipole-dipole interactions become less important. But at low temperature, the tendency to form something that is ordered is going to win, and you end up with something that is very nice ordered that lead to decrease in the configurational energy. So the result of that is that whenever you have molecules that have a strong dipole moment, they will show differences compared to common substances at low temperature, but that as you heat them up, their behavior is going to be more and more similar to what happens for the most common substances. Okay? Now, this equation here, which is a lot of red now, but it was written for a specific relative orientation of these two dipole moments. In reality, because of this thermal motion, what happens when you have a system with many molecules is that all of these dipole moments keep rotating. And somehow we need to figure out what is the average interaction between these dipole moments that rotate. So the way to do that, we will learn more about the reason for it when we talk about statistical mechanics. But the way to do it is to keep in mind that the configurations for which the energy is lower, they're going to have a larger probability to being observed. If you think about the definition of the equilibrium is the system that has lower energy, right? So by taking into consideration that there is a larger probability of observing systems that have lower energy and lower probability of observing the other ones, people have been able to demonstrate that you can find relatively simple descriptions of the dipole-dipole interaction potential. So this is the dipole-dipole interaction potential after taking into consideration of this Boltzmann distribution of the probabilities, which is, those interactions that have lower energy are going to be more favorable. And what you see is that, first of all, this is an expansion. So here we only have the first term. There are going to be other terms here that will be, in general, less important, but in some cases they can become important. What you have is that the sign is negative. Everything else in the equation is going to be positive. So this sign tells you that the dipole-dipole interaction is going to always lead to attractions between the molecules. What you have is that these are all constants. This is the distance between the two molecules to the sixth power. So if you think about it, when we were talking about electrostatic interactions, that same proportionality, it was 1 over r, but now it is 1 over r to the sixth. So when we take two particles and we increase their distance by twice, the electrostatic potential goes down by half, but the dipole-dipole potential goes down by 2 to the sixth power. Right? So essentially dipole-dipole potential goes down much more quickly than the electrostatic interaction. And that's where those range of interactions become important, right? Then you have something that you did not have in the electrostatic interactions, which is the temperature. So what you see is that as the temperature goes up, the dipole-dipole potential goes down. And the reason is that as the temperature go up, you have more of these rotations that are going to average things out, and you are essentially losing the importance of the dipole-dipole interactions at high temperatures. And in the numerator, you actually have the product of the square of the dipole moment of molecule I times the square of the dipole moment of molecule J. So when the two molecules are the same, so water, you now have the fourth power of the dipole moment of water. So now you see that threshold of dipole moment larger or less than 1, it becomes even more important now, because if the dipole moment of water is, so the dipole moment of carbon monoxide was 0.1, so the dipole-dipole interaction between two carbon monoxide molecules becomes proportional to 0.0001. So it becomes very, very small. Okay? Whereas the dipole moment between two ammonia molecules, it was approximately 1.8. So let's assume 2. It becomes 2 times 2, 4, times 2, 8, times 2, 16. So it becomes much more significant compared to the dipole-dipole interaction for molecules that don't have a large dipole moment. Okay, so that's quite important. So these are a few questions as a quiz that we can discuss during the tutorial. So take a look at them and think about what this, hopefully they will help you bring things together. All right, next we have induced dipoles. So we have discussed so far electrostatic interactions where there is a net charge, dipole-dipole when there is a net dipole moment. Many molecules, they don't even have a net dipole moment. However, they do have a proton, they do have their nucleus, and they do have their electronic cloud. When they are exposed to an electric field, what happens is that electronic cloud can be distorted a little bit, and the result of that is that there is going to be an induced dipole moment. And of course, that induced dipole moment is going to be reacting to the electric field and perhaps, interacting with other dipole moments that are in the system. So this is the induced dipole moment, and we will see in a minute that this can lead to interactions between molecules. The way to express this induced dipole moment, it's indicated with mu with a prime to differentiate it from the dipole moment that is intrinsic of a molecule. We multiply the polarizability, which is a property of the molecule, times the applied electric field. So, this is something that the electric field is something that you apply from the outside. So it can be small, it can be large, but the polarizability is the property of the molecule. So if you want, the polarizability is a measurement of how much a molecule is going to express a dipole moment when it is exposed to an electric field. And in this table, there are a number of polarizability of a few molecules. It's the table 4.3 from the Prausnitz book. And what you see is that the polarizability of small molecules like hydrogens are relatively small in those units, but they can become large when we are looking at bigger molecules. And the reason for that is that when the molecules are small, the electrons are very close to the nucleus, and as a consequence, there is a strong electrostatic attraction between the charges. And when we take an external electric field, it's very difficult to distort this electronic cloud. But if we look at a much larger molecule, in this case, some of the electrons are going to be very, very far from the nucleus, and as a result, they will be much more responsive to external electric field, so the polarizability becomes larger. Okay, now two molecules that have significant polarizabilities can only interact with each other if they are exposed to external fields. So the way to express this is to look at this equation that tells us what is the induced dipole interaction. And what you see here is that there is the two molecules are I and J, they are separated by distance r. All right? So here you got the polarizability of molecule I, and here you got the polarizability of the molecule J. And you see that the polarizability of I multiplies by the dipole moment of molecule J to the square. And the polarizability of J multiplies by the dipole moment of I to the square power. So essentially, the dipole moment of one molecule is inducing a dipole moment on the second molecule. And that's why there is this interaction. And you see that the two effects are going to have a sum. If you don't have dipole moments to start with, if the mu's are equal to 0, then you don't have the induced dipole moments, and as a result, you don't have induced dipole interaction. Okay? If you have direct, okay, let's stop the ifs. You have a minus in front. All the other terms are positive, so again, the induced dipole interaction is going to be giving you an attractive interaction. These are all positive constants, and this one here is the distance to the sixth power. So don't get confused by the way I wrote this equation. This distance to the sixth power is in the denominator. So again, as it was the case for dipole-dipole interaction, the induced dipole interaction scales with 1 over r to the sixth. So it becomes smaller as the distance increases between the two molecules. So the resultant force is always attractive, becomes very small as the distance increases. Notice that as opposed to the dipole-dipole interactions, we don't have a temperature effect here. The reason is that these interactions are always there. They may be very small, but they do not depend on temperature. All right. The next type of forces are going to be the dispersion forces. And the reason for this, if we take methane, if we put a lot of methane molecules in a box, the methane does not have a net charge. It does not have a net dipole moment. If that box is not exposed to an external electric field, there is not going to be an induced dipole moment. Yet, we do know that there are going to be interactions between those molecules. And the reason, so what is the source of these interactions? Well, the reason for those interactions is that on average, the electronic cloud in these molecules is going to be equally distributed, so there is not going to be a net dipole moment in there. But instantaneously, you are going to have that the electrons accumulate in specific locations in this geometry. So instantaneously, you're going to have a small dipole moment in these molecules. So this little dipole moment is going to induce a dipole moment on other molecules, and these effects that we just discussed are going to be manifested into some sort of attractions, and these attractions are known as the London dispersion forces. Okay? The equation to describe them is here, where r is the distance between the two molecules. Again, we have molecule I, molecule J, separated by a distance r. So alpha, I, and J are the polarizability of the two molecules. R is the distance. These are all the usual constants that we have. This is the division between them. We have a negative sign at the beginning. So again, we have always attractions between the molecules when they are subject to London dispersion forces. And here we got some terms that describe, again, the properties of the molecules. So as opposed to the alpha, which was the polarizability, these I's are the first ionization potentials of the molecule I and J, respectively. In the case when I is J, so in the case of methane, this equation simplifies into this one. You can convince yourself that it is pretty much the same. And what you see is that you have a negative sign here. You have the product of the square of the polarizability times the first ionization potential. And then in the denominator, you got the sixth power of the distance. So what are these ionization potentials? Well, it's the amount of energy that you need to provide to a molecule if you want to strip the first electron out of it. It's an intrinsic property of the molecule, and some of the values are reported in this table from table 4. And what you see here is that for a small molecule like hydrogen, the first ionization potential in those units is 15.4, whereas for a larger molecule, the first ionization potential is smaller. So you see that there is a proportionality, so to speak. The smaller the molecule is, the larger the first ionization potential is going to be. And the reason for that is again due to the distance between the electrons and the nucleus. When the molecule is small, the distance is going to be limited, and it's going to take a lot of energy if you want to remove one of those electrons from the molecule. What's important to notice is that this factor, the square of the proportion of the polarizability, so alpha squared times the ionization potential, is approximately of the same order of magnitude for most of the molecules you are interested in. You can take a look and try to do the analysis, and you will see that, yeah, it changes, of course, between if you look at methane versus water, but the order of magnitude does not change too much. What that tells us is that the dispersion interactions, they are always there, and they are similar for molecules, for all molecules. So that's something that we got to keep in mind, right? And the last thing that I should notice is that we don't have a temperature here. So these interactions are always there, irrespectively of the temperature. Okay? Very good. So now we have discussed electrostatic interactions, which are those that we understand the best, but we'll leave them there for a minute. And then we have looked at dipole-dipole, induced dipole, and dispersion forces. All of these three interactions, they scale with the inverse of the 6th power of the distance. And they are all giving you attractive potentials. They all depend on the properties of the molecules. Only the dipole moment depends on the temperature. Okay? So a natural question that can come up is, okay, which ones of these are most important? So to analyze which one is more important, let's assume a fixed temperature, 300 Kelvin, so that we can fix a number there. All right? And then what we can do is to take out the r to the 6th, because all of these forces, all these potentials are going to scale with 1 over r to the 6th. So we can ignore that for a minute and just consider the rest of the formulas. And let's also ignore the minus in front, because we know all of these are going to give us attractions. So we just put the rest of the equations in a table for a bunch of different molecules. And that's what Prausnitz did. 300 Kelvin. These are the molecules that were considered. So you got here carbon monoxide, methane, you got water, ammonia, and a few others. Here you got the properties of the molecules, so the dipole moment specifically. And then here are the B's for the dispersion interactions, induced dipole, and dipole-dipole interactions. And these are the values for those B's for the various molecules. And what you see is that when the dipole moment is equal to 0, the dipole-dipole and induced dipoles are going to be 0. When the dipole moment is less than 1, those interactions remain very small. But when the dipole moment is larger than 1, so for these 4, those interactions become important. Okay, so we are already learning that induced dipole, and dipole-dipole interactions are only important when the dipole moment is larger than 1. We expected that before, but now we see it. And it becomes even more evident when we compare these interactions compared to the dispersion forces. These are in this last column. Hold on just a second. And what you see in this last column is that you always have relatively large numbers. And even so, when the dipole moment was 0, the dispersion force is still 100. In this case, it's 1400. Even here, where the dipole-dipole interaction is 1200, the dispersion force is still close to 500. Okay, so in all cases, the dispersion forces are, as a minimum, of the same order of magnitude of the other interactions. So we can never neglect the dispersion interactions. We can neglect the dipole-dipole interaction when the dipole moment is less than 1. And in general, we can neglect the induced dipole if we need to, because in general, they don't really count too much. However, in some cases, they can be significant. Okay, so that's where this table becomes important, because it gives us a feeling of what we can ignore and what we need to keep in mind. And these are a few more questions for a quiz that we can discuss. All right. So the next section had to do with repulsions. And the issue with repulsion is that we understand it a little bit less. We know that it comes from the electronic clouds. When we take two molecules and we push them one against the other, these two molecules start to repel each other, and that's where the repulsion comes from. However, we don't have a mathematical formulation for these repulsions. In reality, if we do ab initio calculations, what we find is that it should be an exponential curve that describes this repulsion. But all we know in general is that it is very short-ranged and it can be very, very strong. So what we typically use is an equation that looks like that, in which this is a constant, and this positive constant becomes smaller as the distance increases to the n power of the distance. And to make sure that the distance effect becomes very important, what we have is that n should be somewhere between 8 and 16. All right? So now that we have some sort of an equation that describes both attractions and repulsions, we can put everything together. And we can look at a general potential that describes interaction between molecules, attractive potential plus repulsive potential. I invert, so this one here is the repulsion, and this one here is the attraction. A, B, and M are all positive constants. The R is the distance. And what we typically assume is that M is close to 6, or in general it's equal to 6, because typically it is a consequence of dispersion interactions. And what we want is that this N should be a number that is larger than 9. Okay? That is the Mie potential, because it just brings everything together. And it turns out that you can put some values in there. And if you are assuming that sigma is the separation at which the potential is 0, so to some extent that sigma is related to the size of the molecule. And if you are assuming that epsilon is the value of the minimum of that potential, then you can recast that equation into this one. It is, a little bit more complex perhaps, but now you have a meaning for this epsilon. You have a meaning for that sigma. And if you are assuming that n is equal to 12 and m is equal to 6, you recover this equation, which is much more familiar. It's the 12-6 Lennard-Jones potential, where epsilon again is the minimum of the interaction potential, and sigma is the distance at which that potential goes to 0. And in fact, when sigma is equal to r, this becomes equal to 1. This becomes equal to 1. 1 to the 12 and 1 to the 6 remain 1. So 1 minus 1 is 0. And you see that your potential goes to 0 when the distance between the two molecules is equal to sigma. To give you a little bit of a feeling of what happens when you change the parameters n and m, here I kept m equal to 6, so to reflect the long distance attractions between the molecules that reflect these dispersion forces. But the n that reflects the short distance repulsion, I changed it from 18 down to 9. And what you see is that when you increase n, you make this portion of the curve steeper, so you have stronger repulsive forces at short separations. Remember that the force is minus the derivative of the potential, so the steeper the curve is, the stronger the repulsive force will be. At large separations, what you have is that the smaller the parameter n is, the longer range the attractions are. Okay? And what happens is that you are changing also the position of the minimum of the potential that gets closer and closer between the two particles as the parameter n becomes bigger. Okay? So now you have a little bit of a feeling of what these potentials look like. Now, we have discussed a lot about various potentials, what they can look like. So what we would expect is that, well, now we understand how molecules interact with each other. And that's why I bring this paper from Science, is now a few years old. And what they did there, they were looking at the structure of benzene, so a fairly common organic liquid. and they were looking at the experimental structure as well as the predicted structure using ab initio simulations to describe the interactions between the molecules. And what they found was that, well, if you want to be within the experimental error that is consistent with the experiments, you need to have very accurate ab initio type of calculations. So it is possible to predict the crystal structure of benzene, or now it was possible 4 or 5 years ago already, but you need to go and use ab initio calculations to get it. So the parameters, the type of potential that I have discussed so far, they are very crude representations, much cruder compared to what is the outcome of an electronic structure calculation. So the message is all of these are approximations. Keep that in mind, but they hopefully help us to understand what are the driving forces that lead to more interactions between the molecules. All right, the last part has to do with hydrogen bonding. The joke is always whenever we don't understand something that has to do with water, we say, well, it must be because of hydrogen bonds. So we don't really understand completely the hydrogen bond. Of course, we know something about it, but there are many things that are a consequence of it that we don't understand much. It leads to interactions between molecules that are quite strong, much stronger compared to the dispersive interactions, but not so strong compared to covalent bonds. So they are somewhere in between. And if you take a look at the Prausnitz's book, what it tells you is that if you want to describe the vapor-liquid equilibrium for fluids such as HF, the hydrogen fluoride, the one way to describe those is to assume that in the gas phase you actually have macromolecules that bring together 6 of these HF molecules together. So it's one way to, so basically it's trying to figure out why systems behave differently compared to what we think they should be behaving. They are very important in nature. They are responsible for how DNA folds. They are responsible for the protein's behavior. They're probably responsible for how effective COVID-19 is. And hopefully they will be responsible for finding a cure to COVID-19. So they're extremely important in nature. They drive self-assembly, protein folding. So all of those are extremely important phenomena. Regarding the strength, in the energy of one hydrogen bond is on the order of 8 to 40 kilojoules per mole, depending on what is the system that forms that hydrogen bond. This is the hydrogen bond in water, so approximately 8 kilojoules per mole. When you have a covalent bond, it's on the order of 2 to 400 in the same units. So it's not nearly one covalent bond. But in water, you have many hydrogen bonds, and one water molecule can engage at the same time with up to 4 hydrogen bonds. So, it becomes a significant amount of energy if you include all the possible hydrogen bonds that the system can form. The effect of hydrogen bonds depends on temperature, and as the temperature increases, you have a lot of rotations, and the result of that is that the hydrogen bond is more important at low temperatures. So to give you an example, this is taken from Prausnitz's book. These are 2 molecules, ethanol and dimethyl ether. If you look at the atomic composition, it's the same. They both have 2 carbon atoms, 6 hydrogens, and 1 oxygen. But the difference is that the ethanol has this part of the molecule here that allows it to form hydrogen bonds, whereas the ether does not. Right? The practical consequence of that is that ethanol is highly soluble in water. It is a liquid at ambient conditions. And ether, on the other hand, is not soluble in water, only a very little amount. And at ambient conditions, it's already a gas. Okay? So these are the quantities. The normal boiling point of ethanol is 78 Celsius. The other one has minus 25, so it's a gas at ambient conditions. The entropy of vaporization is very high for ethanol because when you go from liquid to the gas, you got to break a lot of hydrogen bonds. And its solubility in water, it's infinite. And this is actually a problem. If you happen to drink wine, beer, or any of those things in large amounts, the next day typically you will wake up with a headache, and this, believe me, will become more and more prominent as your own age gets older, so this never stops. And the reason for that is that when we drink those type of drinks, they have some ethanol in them, and the ethanol likes water. So what it does, it takes water away from the brain, and as a result, we are dehydrated and we feel a headache. Right? So that's where the headache comes from. So it's important to understand interactions between molecules. The other type of force that I wanted to bring up are the solvation forces, and these have to do with how small molecules, the solvent, pack around two larger molecules, the solutes, when these solutes are in a dispersion. They are, typically what they give us are force that are, this will be the potential, this is the distance, as a multiple of the diameter of the solvent molecules. And typically what you have is that you have attractions when there is a region where there is not enough space for a fixed layer of solvent molecules, but you have strong repulsions when you have one layer, for example, because it becomes very difficult to remove that last layer of solvent molecules. And here you have two layers, for example, of solvent molecules. The analogy that I always make here is that when we are, when we were before COVID going to social gatherings and we wanted to reach, for example, the bar, or somebody wanted a drink, we wanted to get to a bar, and we are in a crowded environment. So the crowd is what creates the solvent, and everybody wants to get to the same final point, which is talking to the bartender. And every time that you want to get there, you need to displace all the other people that are in between you and the bartender. And there is always a force that you need to impose on those people if you want to move forward. And the moment there is less than an integer number of people in between you and the bartender, somebody behind you is going to push you. That's the source of the attractions, push you closer, but then you're bumping into the next layer, and that's the source of the repulsion. All right, that's where they come from. We don't really use too much of these in the model, but they are very important if we want to study the stability of systems that contain nanoparticles. So in the case of carbon nanotubes, this is a paper from MIT, but we have many papers, our own group, on this same subject, that carbon nanotubes, we want to use them for many different applications, sensors, glucose sensors, cancer diagnostic and therapy, and so on and so forth. For all of those applications, the nanotubes should have been made soluble in water, but they're based on carbon. And as a consequence, they like to agglomerate. So one strategy was to cover them with surfactants, so that when they get to approach each other, these surfactants effectively repel each other by these type of solvation forces. All right? So this is one strategy and one possible application. In this other paper that I left in the Moodle page for you to take a look at, people are looking at membranes, of cellular membranes, and they're trying to understand how the different proteins in those membranes are interacting with each other and how they're moving throughout the membrane. And this is a very important topic because speaking of COVID attacks different cells via recognition between the membranes of the cells. So how the proteins are expressed on the surface of the COVID versus other cells is going to dictate how it approaches and assembles with a different cell. So understanding that will be useful. And also these proteins that you see with the hole, they are channels effectively that control the transport of water or the transport of ions through the cells. And one important ion channel is responsible for our ability to feel pain. And there is evidence, there was a science paper from a good number of years ago that a family, it was a Pakistani family, everybody in that family was not able to feel pain. It was an hereditary disease. And the reason for that disease was there was a malfunction in one of the ion channels in that family, and it was not able to allow for sodium, if I remember correctly, transport in and out of the cells. So transporting ions through the cells is one of the mechanisms by which we communicate pain to our brain, and vice versa, how our brain controls the rest of the body. So these are important things, and if we want to understand them, we need to understand how the interactions between the molecules happen. Few more questions for a quiz, just to summarize what we discussed. And before I end, I wanted to bring up the hydrogen bond again. This is the current definition from the IUPAC. And what you see here is that D does not necessarily have to be an oxygen. So we can have hydrogen bonds between substances that are different than water. And what I want to do now is to give you a little bit of a history of science, because the first person that gave the possibility that the hydrogen bond was forming between substances different than just water, but very general, was this person Suter. And I ask you, do you think that was a man or a female? And think about the answer to that, and we'll get back in just a minute. So these papers were published in the 60s, and this type of bond was proposed to explain experimental evidence. And these are the texts that were taken from those papers. Notice that to be able to support those propositions, it was necessary to measure this type of distances, and we are talking about 50 years ago. Okay, these are fractions of a nanometer difference that this person was able to measure in a few cases. Now, a few years later, this other person from California wrote a book, a very famous book, and apparently this book was in every crystallographer around the world, in every office. And the last chapter, one chapter in that book has this title over here. What is this hydrogen bond? And at the end of the chapter, this person concluded with, this is not an hydrogen bond. And this person, as opposed to the person in the prior slide, this person was very famous because he had worked with Watson and Crick, so he was related to the discovery of the DNA. And again, his book was used throughout the world. Because of the influence of this book, people started to be scared about using the definition of hydrogen bonds for this type of bonds. And actually, instead of calling them hydrogens, they started calling them suitors, because there was evidence that they were real, but they did not want to get into trouble with this prominent person that decided that they should not happen. Okay, so the whole community got biased against this possibility of having that type of hydrogen bonds. Until in the 70s, so 10 years after the original publications, these two other people reviewed all the literature, all the experimental data, and they finally found evidence that these were indeed hydrogen bonds, because there was a clear difference in the bonds in the crystallographic stages. But over 10 years went by, and the whole concept was basically put on the fridge for 10 years. So you can imagine how much of a delay that caused the community. So the point here is that whenever you will become a very famous scientist, and you will have your opinion, of course, and you will make your mistakes, and you will make your discoveries like everybody else does. But if you are particularly influent, make sure you're not putting down somebody else's opinion unless you are completely clear about it, because there is the risk of inducing a bias in the literature, and that bias can be quite significant. Anyways, the reason I like this part of the history of science is that this Suter, her name was June, and she was born in 1929, New Zealand, and she actually was a member of the UCL community. She was a postdoc working with Kathleen Lonsdale in crystallography. And, after writing those couple of papers on hydrogen bonds, she got interested in something else, and she was studying Napoleon III bladder when the person from California was making that big noise. So at that point, she didn't care anymore. And this is a picture. And she also became interested in computational chemistry, although that was after her vision was deteriorated. And so basically, when she could not do experiments anymore, she started to do computations. So she's a leading scientist, a member of the UCL community, and she introduced this concept of hydrogen bonds that is now adopted by the wide community, and it is an example of a person that has made a difference in the history of science. All right, with this, I conclude my brief and fast review of the second topic, and maybe I stop recording.